Hey everyone, and welcome to today's Explainer. I am so pumped you're joining us. Look, we're going to tackle a foundational math concept today that, honestly, sometimes trips people up. Math anxiety is a very real thing, and let's face it, long division is nobody's best friend. But today, we're going to make things incredibly simple. We're diving into square roots. And we aren't just going to look at the boring, traditional, textbook way of finding them. No way. We're going to uncover a really cool, almost magical mathematical trick to find square roots using just simple subtraction. So get ready to see numbers in a totally different light. Here is our quick roadmap for today. First, the meaning of a square root. Second, the relationship between squares and roots. Third, finding a square root via subtraction. Fourth, identifying a perfect square. And finally, what happens when numbers aren't perfect? All right, kicking things right off with section 1, the meaning of a square root. So I've got to pose this fundamental question to you right up front before we throw any formulas around. What exactly is a square root? If you had to explain it to someone who had literally never heard of it, what would you even say? Well, let's break down the actual definition. Here's the formal breakdown. If we take any number, let's call it x, the square root of x is simply the number which, when multiplied by itself, gives us that original x as the product. It's usually denoted by that familiar checkmark-style root symbol. So if our target number x is sitting inside that symbol, we're basically just on a hunt for the hidden number that multiplies by itself to give us our target. Let's ground this with some undeniable, everyday examples. We all know that 6 multiplied by 6 gives us 36, right? Therefore, the square root of 36 is exactly 6. When you put 36 inside that root symbol, you're just pulling out the single number that created it. It's the same exact deal for the others. 2 times 2 is 4, so the square root of 4 is 2. 3 times 3 is 9, so the square root of 9 is 3. 8 times 8 is 64, meaning the square root of 64 is 8. Are you noticing a pattern here? Inside the root, we technically have 2 identical numbers multiplying, but we only pull a single one out as our final answer. Moving right along to section 2, the relationship of squares and roots. This inverse relationship is honestly brilliantly simple. If we take 11 and square it, multiplying 11 by 11, we get 121. But if we work backwards and ask for the square root of 121, it acts exactly like an undo button. It brings us right back to our original 11. And it's the exact same concept when we scale up to larger numbers. 14 squared gets us 196. Taking the square root of 196 reverses the operation entirely, landing us perfectly back at 14. They are literally two sides of the exact same mathematical coin. Okay, on to section 3, square root via subtraction. This is where it gets really fun. To understand why this trick works, we have to look at this totally beautiful pattern hiding right there in odd numbers. The rule is this. The sum of the first n consecutive odd natural numbers is always exactly n squared. Think about it for a second. The first odd number is 1. 1 squared is 1. The first 2 odd numbers are 1 and 3. 1 plus 3 is 4, and 2 squared is 4. How about the first 3 odd numbers, 1, 3, and 5? Add them up. 1 plus 3 is 4 plus 5 is 9. And what's 3 squared? It's 9. It turns out, every single square number can be expressed as a sum of successive odd numbers starting right from 1. So because squares are built by adding successive odd numbers, we can find square roots by doing the exact opposite. Here's the playbook for our repeated subtraction trick. Step 1, start with your target number. Step 2, continuously subtract successive odd numbers in order. So first you subtract 1, then you subtract 3 from your new balance, then 5, then 7, and so on. Step 3, just count the exact number of steps it takes to hit 0. The number of steps is your square root. It really is that simple. Let's put this into practice with section 4, identifying a perfect square. Let's test out the number 81. We start by subtracting 1, leaving us with 80. Then we subtract the next odd number, 3, dropping us down to 77. Then minus 5, minus 7, minus 9. And as we cascade down these odd numbers, our balance is just dropping lower and lower. Finally, on our 9th step, we take our balance of 17, subtract our next odd number, which happens to be 17, and boom, we hit rock bottom, exactly 0. Now, the absolutely crucial point is right here. How many steps did it take us to hit 0? It took exactly 9 steps. Because we reached a perfect 0 right on that 9th step, the square root of 81 is definitively 9. No guessing, no memorizing times tables, the subtraction proved it to us perfectly. Let's see how this builds with a slightly larger number, like 121. We kick things off by subtracting 1, then 3, then 5. We just keep chipping away with consecutive odd numbers, 7, 9, 11, 13, all the way down. Fast forward to step 11, our remaining balance is 21. We subtract the next odd number, 21, and we land beautifully on 0 once again.
Look at that, 0 again. And what step were we on when that balance hit 0? We were on the 11th step. Therefore, 121 is a perfect square, and its square root is exactly 11. It's just such a satisfying process to watch unfold, isn't it?
But wait, section 5. When numbers aren't perfect, what happens then? Let's apply our trusty method to the number 55. We start chipping away. -1, -3, -5, -7, until we get to step 7, where our running balance is 6. Now, watch this closely. For step 8, our next odd number to subtract is 15, but 6 minus 15 equals -9. We completely blew past 0 and dropped straight into negative territory. Because our balance fell below 0 and gave us a negative number, we've got to firmly declare that 55 is not a perfect square. This trick only works, and a number is only a perfect square, if the balance lands perfectly on 0. If it bypasses 0, you stop right there. It simply doesn't have a whole number square root. Let's run one final test with the number 90. We send it through our odd number gauntlet, subtracting 1, 3, 5, and so on. By the 9th step, we're left with a balance of 9. But for the 10th step, the next consecutive odd number to subtract is 19. 9 minus 19 gives us -10. Once again, we blew right past 0. And there it is again. Missing 0 means it is not a perfect square. Because we landed on -10, we know for an absolute fact that 90 is not a perfect square, and we literally cannot find a whole number square root for it using this method. The math just doesn't lie. What an incredible journey through the hidden logic of numbers. By simply subtracting odd numbers, we were able to peel back the layers and figure out if a number is a perfect square and exactly what its root is. I highly encourage you grab a piece of paper today, pick a random number, and test this trick out yourself. See if you can hit 0. It really makes you wonder, though, if subtracting simple odd numbers can magically reveal square roots, what other fascinating, magical patterns are hiding in the math all around us, just waiting to be discovered? Keep questioning, keep calculating, and keep exploring. Thank you so much for joining me on today's Explainer, and I will catch you next time.